2's complement is a mathematical operation on binary numbers, as well as a binary signed number representation based on this operation. Its wide use in computing makes it the most important example of a radix complement. The 2's complement of an n-bit number is defined as the complement with respect to 2n. In other words, it is the result of subtracting the number from 2n, which in binary is 1 followed by n zeros. This is also equivalent to taking the 1's complement and then adding 1, since the sum of a number and its 1's complement is all 1 bits. The 2's complement of a number behaves like the negative of the original number in most arithmetic, and positive and negative numbers can coexist in a natural way. In 2's complement representation, positive numbers are simply represented as themselves, and negative numbers are represented by the 2's complement of their absolute value. Two tables on the right provide examples for n equals 3 and n equals 8. In general, negation is performed by taking the 2's complement. This system is the most common method of representing signed integers on computers. An n-bit 2's complement numeral system can represent every integer in the range -2 to +, while 1's complement can only represent integers in the range -2 to +. The 2's complement system has the advantage that the fundamental arithmetic operations of addition, subtraction, and multiplication are identical to those for unsigned binary numbers. This property makes the system both simpler to implement and capable of easily handling higher precision arithmetic. Also, 0 has only a single representation, obviating the subtleties associated with -0, which exists in 1's complement systems. History. The method of complements had long been used to perform subtraction in decimal adding machines and mechanical calculators. John von Neumann suggested use of 2's complement binary representation in his 1945 first draft of a report on the EDVAC proposal for an electronic, stored program digital computer. The 1949 EDSAC, which was inspired by the first draft, used 2's complement representation of binary numbers. Many early computers, including the CDC 6600, use 1's complement notation. The IBM 700 and 7000 series scientific machines use sign, magnitude notation, except for the index registers which are 2's complement. Early, commercial 2's complement computers include the Digital Equipment Corporation PDP-5 and the 1963 PDP-6. The System 360, introduced in 1964 by IBM, then the dominant player in the computer industry, made 2's complement the most widely used binary representation in the computer industry. The first mini-computer, the PDP-8 introduced in 1965, uses 2's complement arithmetic as do the 1969 dated General Nova, the 1970 PDP-11, and almost all subsequent mini-computers and microcomputers. Potential ambiguities of terminology. The term 2's complement can mean either a number format or a mathematical operator. For example, 0111 represents decimal 7 in 2's complement notation, but the 2's complement of 7 in a 4-bit register is actually the 1001 bit string, which is the 2's complement representation of -7. The statement, convert x to 2's complement, may be ambiguous, since it could describe either the process of representing x in 2's complement notation without changing its value, or the calculation of the 2's complement, which is the arithmetic negative of x if 2's complement representation is used. Converting from 2's complement representation. A 2's complement number system encodes positive and negative numbers in a binary number representation. The weight of each bit is a power of 2, except for the most significant bit, whose weight is the negative of the corresponding power of 2. The value w of an n-bit integer is given by the following formula. The most significant bit determines the sign of the number and is sometimes called the sign bit. Unlike in sign and magnitude representation, the sign bit also has the weight minus shown above. Using n bits, all integers from minus to 2n minus 1 can be represented. Converting to 2's complement representation. In 2's complement notation, a non-negative number is represented by its ordinary binary representation. In this case, the most significant bit is 0, though the range of numbers represented is not the same as with unsigned binary numbers. For example, an 8-bit unsigned number can represent the values 0 to 255. However, a 2's complement 8-bit number can only represent positive integers from 0 to 127. Because the rest of the bit combinations with the most significant bit as 1 represent the negative integers -1 to -128. The 2's complement operation is the additive inverse operation, so negative numbers are represented by the 2's complement of the absolute value. From the 1's complement to get the 2's complement of a binary number, the bits are inverted, or flipped, by using the bitwise not operation. The value of 1 is then added to the resulting value, ignoring the overflow which occurs when taking the 2's complement of 0. For example, using 1 byte, the decimal number 5 is represented by 0000 or 1012. The most significant bit is 0, so the pattern represents a non-negative value. To convert to -5 in 2's complement notation, the bits are inverted, 0 becomes 1, and 1 becomes 0. 1111, 1010. At this point, the numeral is the 1's complement of the decimal value -5. To obtain the 2's complement, 1 is added to the result, giving 1111, 1011. The result is a signed binary number representing the decimal value -5 in 2's complement form. The most significant bit is 1, so the value represented is negative. The 2's complement of a negative number is the corresponding positive value. For example, inverting the bits of -5 gives 0000 or 100, and adding 1 gives the final value 0000 or 101. The 2's complement of 0 is 0. Inverting gives all 1's, and adding 1 changes the 1's back to 0's. Furthermore, the 2's complement of the most negative number representable is itself. Hence, there appears to be an extra negative number. Subtraction from 2n. The sum of a number and its 1's complement is an n-bit word with all 1 bits, which is 2n minus 1. Then adding a number to its 2's complement results in the n lowest bit set to 0 and the carry bit 1, where the latter has the weight 2n. Hence, in the unsigned binary arithmetic, the value of 2's complement negative number x asterisk of a positive x satisfies the equality x asterisk equals 2n minus x. For example, to find the 4-bit representation of -5, x equals 510, therefore x equals 01012. Hence, with n equals 4, x asterisk equals 2n minus x equals 24 minus 510 equals 100,000, and 2 minus 01012 equals 10,112. The calculation can be done entirely in base 10, converting to base 2 at the end. X asterisk equals 2n minus x equals 24 minus 510 equals 1110 equals 10,112. Working from LSB towards MSB, a shortcut to manually convert a binary number into its 2's complement is to start at the least significant bit, and copy all the zeros until the first one is reached, then copy that one, and flip all the remaining bits. This shortcut allows a person to convert a number to its 2's complement without first forming its 1's complement. For example, the 2's complement of 0011, 1100 is 1100 or 100, where the underlined digits were unchanged by the copying operation. In computer circuitry, this method is no faster than the complement and add 1 method. Both methods require working sequentially from right to left. Propagating logic changes. The method of complementing and adding 1 can be sped up by a standard carry look-ahead adder circuit. The LSB towards MSB method can be sped up by a similar logic transformation. Sign extension. When turning a 2's complement number with a certain number of bits into one with more bits, the most significant bit must be repeated in all the extra bits. Some processes do this in a single instruction. On other processes, a conditional must be used followed by code to set the relevant bits or bytes. Similarly, when a 2's complement number is shifted to the right, the most significant bit, which contains magnitude and the sign information, must be maintained. However, when shifted to the left, a 0 is shifted in. These rules preserve the common semantics that left shifts multiply the number by 2 and right shifts divide the number by 2. Both shifting and doubling the precision are important for some multiplication algorithms. Note that unlike addition and subtraction, precision extension and right shifting are done differently for signed versus unsigned numbers. Most negative number, with only one exception, starting with any number in 2's complement representation, if all the bits are flipped and 1 added, the 2's complement representation of the negative of that number is obtained. Positive 12 becomes negative 12, positive 5 becomes negative 5, 0 becomes 0, etc. The 2's complement of the minimum number in the range will not have the desired effect of negating the number. For example, the 2's complement of -128 in an 8-bit system results in the same binary number. This is because a positive value of 128 cannot be represented with an 8-bit signed binary numeral. This phenomenon is fundamentally about the mathematics of binary numbers, not the details of the representation as 2's complement. Mathematically, this is complementary to the fact that the negative of 0 is again 0. For a given number of bits k, there is an even number of binary numbers 2k. Taking negatives is a group action on binary numbers. And since the orbit of 0 has order 1, at least one other number must have an orbit of order 1 for the orders of the orbits to add up to the order of the set. Thus some other number must be invariant under taking negatives. Geometrically, one can view the k-bit binary numbers as the cyclic group, which can be visualized as a circle, and taking negatives is a reflection, which fixes the elements of order dividing to 0 and the opposite point, or visually the zenith and nadir. Note that this negative being the same number is detected as an overflow condition since there was a carry into but not out of the most significant bit. This can lead to unexpected bugs in that an unchecked implementation of absolute value could return a negative number in the case of the minimum negative. The abs family of integer functions in C typically has this behavior. This is also true for Java. In this case, it is for the developer to decide if there will be a check for the minimum negative value before the call of the function. The most negative number in 2's complement is sometimes called the weird number, because it is the only exception. Although the number is an exception, it is a valid number in regular 2's complement systems. All arithmetic operations work with it both as an operand and a result. Why it works. Given a set of all possible n-bit values, we can assign the lower half to be the integers from 0 to inclusive and the upper half to be -2n-1 to -1 inclusive. The upper half can be used to represent negative integers from -2n-1 to -1 because, under addition modulo 2n, they behave the same way as those negative integers. That is to say that because I plus j mod 2n equals I plus mod 2n, any value in the set j plus k2n, k is an integer, can be used in place of j. For example, with 8 bits, the unsigned bytes are 0 to 255. Subtracting 256 from the top half yields the signed bytes -128 to -1. The relationship to 2's complement is realized by noting that 256 equals 255 plus 1, and is the 1's complement of x. Example -95 modulo 256 is equivalent to 161 since -95 plus 256 equals -95 plus 255 plus 1 equals 255 -95 plus 1 equals 160 plus 1 equals 161 1111 1111 255 -0101 1111 minus 95 1010 0000 160 plus 1 plus 1 1010 0001 161. Fundamentally, the system represents negative integers by counting backward and wrapping around. The boundary between positive and negative numbers is arbitrary, but by convention all negative numbers have a leftmost bit of 1. Therefore, the most positive 4-bit number is 0111 and the most negative is 1000. Because of the use of the leftmost bit as the sign bit, the absolute value of the most negative number is too large to represent. For example, an 8-bit number can only represent every integer from -128 to 127 inclusive. Negating a 2's complement number is simple. Invert all the bits and add 1 to the result. For example, negating 1111, we get 0000 plus 1 equals 1. Therefore, 1111 must represent -1. The system is useful in simplifying the implementation of arithmetic on computer hardware. Adding 0011 to 1111 at first seems to give the incorrect answer of 10,010. However, the hardware can simply ignore the leftmost bit to give the correct answer of 0010. Overflow checks still must exist to catch operations such as summing 0100 and 0100. The system therefore allows addition of negative operands without a subtraction circuit, and a circuit that detects the sign of a number. Moreover, that addition circuit can also perform subtraction by taking the 2's complement of a number, which only requires an additional cycle or its own adder circuit. To perform this, the circuit merely pretends an extra leftmost bit of 1 exists.